we're already one day past when I was supposed to finish fluids, so I'm behind, but I have to cover some things in fluids. We've already talked about density and pressure. We haven't talked about buoyancy or Archimedes' principle or pressure in a gas. We have talked about atmosphere. And so we have basically those things to talk about before I get on to the next topic. And before we do even that, I want to talk a little bit about the homework, at least one problem I was talking to a student beforehand about, and I wanted to, okay, let me check. Is anybody not here? 2, 4, 6, 8, 10, 12, 14, 16, 18. No, we're all here. And that's the one with the bucket swirling around in a circle. Did anybody actually try this at home?
No, but
okay, no water involved, but here's the basic idea. I have this little bob, which I can swing back and forth, but I can swing it around a circle and it stays in a circle. Now, of course, what will happen if I slow down? It doesn't make it all the way if I slow down. So there's a certain speed I have to maintain for it to stay in a circle. Now, along with this, what happens if I let go of the string? What direction is it going to go? What's it going to do? Okay. Go straight in whatever direction. Now, let's make sure we understand that. Let us say that I let go when it is directly vertical, when the bob is above my hand. What direction will it travel then? Okay? Being scientists, you say, I see the ball going around, and let's go. I know it's going to fly away. I think it's going to fly, what direction? Straight up. And my reason is, my hypothesis needs to have a reason based on science. Okay, there said gravity. Well, let's do the next step. Let's do the experiment. So now I've got it wrapped around my thumb. That won't work. Okay, so I'm going to let it go when it's directly here to the best of my abilities. Now, I'm not perfect at this. Now, it went up some, but it didn't go straight up. And you know what? The truth is, I let go too early. It's bad that's why when you do these things right, you have equipment that does automatically. There it went more horizontally, less up. If I let it go at the instant it was straight up, what direction was its velocity at that point? Horizontal, at that instant. If I let it go a little early, it has some upward velocity. But if it's perfectly vertical, then its velocity would be horizontal. And when I let it go, it has momentum. It has mass times velocity. As we saw from one of our questions on the last quiz, momentum is, that thing's still on top, isn't it? No, it fell down. Okay, good. Then I'll find it. Momentum is inertia in motion. It has momentum horizontally. What does Newton's first two laws say about its motion? Okay, it'll stay in constant motion if nothing acts on it. So if there was no force of gravity, it would have just kept going like this until it hit the wall. But there is gravity. What did gravity make it do? Fall. So it fell because of gravity. We learned with trajectories that the horizontal motion is independent of vertical. So it's going to go like this at constant speed, but it's going to start dropping. And so the actual path should have been going like that. Yes, here it is right here. So, drawing a picture to go with that, if I'm swinging it around in a circle, so, okay, there's a circle, back to, here's the center of the circle. If I let it go right here at the top, its velocity is like that. And because of gravity, it's actually going to go something like that. So the horizontal motion stays constant, but the vertical drops. So inertia is going to try to make it go straight, and the force of gravity is curving it. Now imagine that instead of having rubber, I had water there. Water in a bucket. So the bucket is keeping the water from going upward or sideways out of the bucket. It's not keeping it from coming out the open end. Is the water going to fall out of the bucket if the water is moving horizontally, the open end is down? It won't, but gravity would make it start to fall. But if you notice the curves I drew, the circle falls underneath the path that gravity would make it fall out at. And so the bucket actually has to push down to accelerate the water to make it go in the circle instead of going off like this. So without the bucket, the water would follow that green line, but the bucket is pushing down, so the bucket is applying an additional force. I'll call it force of the bucket on the water to make it bend down more than it would have if it was just flying without the bucket around. So it's the inertia of the water that makes it want to keep going in the same path. Gravity's trying to make it go down, but not enough for it to come out of the bucket. The bucket's having to push down more to keep it in the circle. Now, so here's some terms we didn't talk about in class, going back to chapter 4, obviously. Centripetal versus centrifugal. When I was a kid, we're going on the road trip with the fam, and, there's me and my sister, and, well, actually probably me and two sisters in the middle seat. And we go around a corner, and if I am here, so I'm X, and the car goes this way, what do you suppose my sister does? My sister slides into me. Why? According to inertia, what direction is all of our velocities?
6 to 4.
We're all going this direction. When the car turns, according to Newton's laws, according to inertia, what is her motion wanting to do? Keep going straight. But the car is turned out from underneath her, right? And so that's why she slides over into me on those nice vinyl seats we used to have as kids. And so she slides into me and smashes me against the wall. And so I don't like that. So next time around, when the car changes and goes this direction, what's going to happen? I'm going to slide into her. Because I didn't like it, I'm probably going to push off of the wall to push harder on her to make her pay, right? And that's what begins the game of corners. Well, it's the same idea. Really, inertia was trying to keep us going straight, and the car was turning underneath us, and we didn't have enough friction to keep us with the car, and we slid. And so people start saying things like, well, as the car turned, she slid into me because of centrifugal force, the force pushing away from the center. But then in physics, we learn that's not right. There was no force pushing her outward. What made her slide into me? Inertia. Just inertia. Inertia is not a force. It's just a property thing, so why don't you go in a straight line? And then when she hit me, then there was a force of me pushing her back in the same direction the car was going. So I was pushing her toward the center of the circle. Centrifugal means away from the center. But since I was pushing her toward the center, we call that a centripetal. So there is a force toward the center, and we put here the sum of the forces toward the center. We call the centripetal force. Centripetal means toward the center, so obviously it exactly is what it means. Newton's second law says the sum of the forces should be the mass times the acceleration. So that subscript C means toward the center. And it turns out if something's going to go in a circle, it's accelerating, right? Because it's changing direction. And that acceleration, if it's going in a circle, is the speed squared divided by the radius. So the faster something is going in a circle, the bigger the acceleration necessary to keep it in that, circle. And so that's why when I was swinging the bob around, when I went at a slow speed, it didn't stay in the circle because it didn't have a large enough acceleration toward the center necessary. But when I go faster, it needs a stronger acceleration toward the center, stronger than just gravity can provide, and then the tension has to provide the rest. And so with the bucket of water, it's the same thing. As long as you're going fast enough that acceleration v squared over r is bigger than the acceleration of gravity, 9.8 meters per second squared, then the water's going to stay in the bucket. Now, some final things to note. That acceleration, what happens if I make it a shorter string, if r is smaller? What is that going to do to the acceleration necessary to make it go in a circle? If you divide by a small number, what does it do to your answer? Makes it big. So if you're in a small circle, you have to go faster. If it's a large circle, then you're going to have I said that backward. It makes it larger to get g, then you can have a slower speed. So smaller radius, you can have slower speed and stay in a circle. Bigger radius, you have to have a faster speed to stay in a circle. Okay, so that is a big long explanation for the bucket problem. Now, just some other reminders on the homework. Numbers 1 and 5 are essentially the same problem. You have to calculate the force of gravity. Remember, the force of gravity equation that's the universal law of gravitation. That's the law you use to find the gravity between any two objects. And in that equation, G is the gravitational constant, 6.67 times 10 to the minus 11 newtons meter squared per kilogram squared. There was a student who asked about, well, what about lowercase g? Lowercase g is the acceleration due to gravity, which is 9.80 meters per second squared. Notice the units are completely different for the two. They're not exchangeable. They mean completely different things. So you just have to show this. Now, for question 1, if you just put your answer 6.67 times 10 to the minus 11 newtons, how many points is that worth? 1. Right? We want more than 1. So how do you get the full credit? To get the full credit, you write the equation and then you put the numbers in and get your answer. It's not a lot more work, but it shows, yeah, I know how I got that. And then for problem 5, I think it is the which one is greater or ranking them one. You have to calculate the force of gravity between the sun and Mars, the sun and the moon, and the sun and Earth. For the distance between the sun and the moon, just use the average distance between the sun and the Earth. The reason for that is sometimes the moon is closer than the Earth, sometimes it's farther, but its average distance is the same as the average distance of the Earth. So you have to get the mass of the sun, the mass of the Earth, the mass of the moon, the mass of Mars, and the separation between the sun and Earth and the separation between the sun and Mars. Question?
Can we just take a really quick look at number 9?
Number 9. Sure, just tell me what it is.
It's about the water flowing out when you raise a fill glass.
Okay, that's something that should come through in today's lecture. If it doesn't, bring it up again, okay? Don't forget. I won't, trust me. Okay, so getting to the water ideas then. Why do we have water towers? It's not so we could come out here and put, Richard plus Amy on the clock tower or the water tower. That's not the purpose, right? The purpose is to have the water at a higher elevation so it has higher potential energy. If it has higher potential energy, it's going to be able to come down lower and do work. Of course, in this chapter, instead of talking about potential energy, we just talk about the water pressure it develops. Do you remember the equation we had from last class period about the water pressure, how it changes with height? Going with a no there?
Yes.
Yes. The difference in pressure is equal to the density of the water times the acceleration of gravity multiplied by the height of that tower. So the taller the water tower, the higher the pressure. So one of the few memories I have of living in Liberia is that we had our water tower was on the roof of our house. So the bottom of the water tower was about 8 feet off the ground, and the top was about 10 or 12 feet off the ground. What do you suppose that meant for water pressure in our house? Not very high at all. So if we'd raised it up, we would have been able to have higher water pressure, and that's the point of those water towers. So our first of the, oh goodness, there's a way to make this better. I didn't notice it until now. Our first of the clicker questions, which you can answer starting now, is simply, does a 3-meter lake or a 6-meter lake, so we're talking about the depth, exert more pressure on a dam? Jackie's totally down with this, although I can't tell you what answer you gave. Valerie, Stacy. Okay, starting to roll in.
Wait, what's the channel?
The channel is 33, yeah. Okay, we have still Tiffany, Hannah, Vanessa, and Carmen. Hannah and Tiffany. And now it's just Hannah, who is quickly trying to get logged in. I trust you're getting logged in and not texting.
No, I'm not. I'm getting all
And I do want to wait because it does affect your grade, right? It's kind of rude to say, you snooze, you lose. Not yet. Oh, he's logged in and now reading the question. Okay, we've all thought about it, and we have our answers. 3 said the 3-meter, and 15 said the 6-meter pull. So we're grabbing a random card, which is Jackie, our first to answer. What'd you say, Jackie?
I said B because you just said that the higher the tower, the higher the pressure. So I figured the higher the water, the more the pressure.
Okay, that's very good reasoning. The pressure difference between the top of the water level, what's the pressure going to be at the top of the water? It's actually not 0, right? Because we have air pressure out here. So it'd be atmospheric pressure at the top. And then as you go down, it's going to be that density of water, which is 1,000 kilograms per meter cubed. That's the SI unit. Times G, roughly 10 meters per second squared, times the height. So at 3 feet, you have 10,000 times 3 is 30,000 pascals additional pressure. And at 6 feet, 60,000 pascals additional pressure. Now, what is atmospheric pressure? Pressure atmosphere is equal to 1.013 times 10 to the 5th pascals. And these numbers I was saying were times 10 to the 4th. If you want to get to 1 atmosphere, that is if you want to get to 100,000 pascals, how deep are you going to have to go in the water? It's 10,000 pascals per meter. What's 100,000 divided by 10,000? 10. So at a depth of 10 meters, you'll actually have increase the pressure by 1 atmosphere. So that's a rule of thumb that divers use. Every 10 meters or roughly every 30 feet, the pressure goes up by an atmosphere. And so Jackie gave us exactly the right answer here. The pressure is going to increase. Now, if we look at the surface of the dam, at the bottom where the pressure is higher, that means the force per unit area is higher, so it's pushing on the dam harder. And so the dam is going to need to be stronger at the bottom because you have more force per unit area. Notice also the curvature of the dam. It's curving in. Why do you suppose it does that? I will give you a hint. What direction does the force that the water pressure applies go?
Like the very corner? Or...
Well, it goes normal to the surface. That is directly into it. So the force is going like this. So the reason for curving is so the force is pushing the dam down so that it's less likely to move, right? If you had it curved the other way, if you made your dam so it was curved like this, then the water would push up on it and tend to lift it and move it, right? But if it pushes down, it's going to push it into the earth and it's less likely to be moved by the water. Okay, buoyancy. Question, Brittany.
Okay, so you just said that the pressure is greater on the bottom
Yes.
because of surface area.
Well, the pressure is greater because of depth. And so the force per unit area is pressure. So the force that's going to be applied to a small piece is bigger here than here because it has higher pressure, because it has greater depth. Buoyancy is a force that's lifting up. I still haven't looked. There better be a buoyancy lab because that's what I want to do in lab tomorrow. A lab where we study buoyancy. And so if we put something like this rock in water, how does the pressure on the bottom compare with the pressure on top?
It's the same.
It's not the same. If it was the same, there would be no buoyancy. It's the pressure difference that makes the buoyancy. If you go to greater depth, what? I didn't hear the...
Never mind.
Okay. Well, what Jackie told me, because I heard Jackie, was at lower depth, I have higher pressure. And so that means I'm going to have higher pressure on the bottom of the rock than I have on the top. And so these arrows are showing the directions of the forces on the rock due to pressure. That force is always straight into the surface, right? That's the force that the liquid, the fluid, is putting on the surface. But because of the higher pressure on the bottom, the forces on the bottom are bigger than the forces on the top. I kind of alluded to this in the last class period. If I have more force pushing up than I have pushing down, what direction is the net force? Up. And so we say there's a force buoying us up, hence the buoyant force. So it turns out the bigger the volume of something, the bigger the buoyant force. So if you have a big rock, it's going to have a bigger force pushing it up. Small rock, less force pushing it up. And in fact, I'm just going to jump right to the chase. The equation for the buoyant force is the density of the fluid times the volume displaced times g. So notice it's not the density of the object, it's the density of the fluid. The weight of the object, the force of gravity, is the density of the object times the volume of the object times g. Notice object versus fluid and object versus displaced. If something sinks, the volume displaced will equal the volume of the object. But if something floats, it won't. If something floats, the displaced volume, that is how much water was moved aside, is less than the volume of the object.
What was that second one?
What second one?
The force of gravity. What was that one?
This here is the weight, right? It says force of gravity here. That's the weight. That's what force of gravity means. So the weight, the density of the object times the volume of the object is the mass, since density is mass per volume. And the density of the fluid times the volume displaced is the mass of the fluid displaced. And that leads us directly to Archimedes' principle, which I have learned when it shows blank, if I change the magnification, it comes back, in case you're wondering why I'm messing with it. Archimedes is the person who discovered this thing about buoyancy. I won't go through the entire story of Archimedes' discovery because of time, but he realized that you can actually determine the density of an object if you measure the buoyant force and how much fluid it displaces. So that's what I hope to do in lab tomorrow. So we'll talk more about Archimedes' principle in lab tomorrow. Hence, going past it because of time. This is basically what we'll do. The picture on top shows an object outside of water, and it's weighed outside of object, and it weighs 3, and it doesn't tell us what the units are. Actually, it says if a 3 kilogram block. If it's 3 kilograms, then it's going to weigh 30 newtons, right? Because kilograms is not a weight. And then if you put it in the fluid, it weighs only 10 newtons, but the amount of water that was displaced weighs 20 newtons. So the weight of the displaced fluid plus the weight when it's in water adds up to its initial weight, because the weight of the displaced fluid is equal to the buoyant force. So the weight that is here in the water that ran out is equal to the amount that is pushing up on the stopper, or whatever that is. So like I said, we'll look at this more in lab tomorrow. Come on, James. And instead, we'll ask this question to make sure we understood. The force buoyant is the density of the fluid times the volume displaced times g, and the weight, the force of gravity, is equal to the density of the object times the volume of the object times g. Just putting those there to help you in case you need them. On which of these blocks, submerged in water, is the buoyant force the greatest? If you leave me now, you take away the big... Oh, no, just coming to get a drink. Then I don't have to go, ooh, ooh. Yeah, Carmen.
Do you have any extra?
I have hundreds of them.
Can I have 10?
All right, everybody, nope.
Let me ask them.
Yeah, pass them around. I want everyone to have plenty. Okay, we're still waiting on...
Yeah. Okay, I was confused.
Okay, this one we didn't have quite the agreement on. Half the people said all the same, and then we had smaller numbers on the others. So turn to your neighbor and discuss the ideas, then we'll repoll, and then Eris can explain it all to us.
I think I have some.
I'm here.
I'm pretty sure it didn't matter about water objects, like how heavy it weighs. They're all, I don't know, that just doesn't.
Well, because Look at the equation. It has the
So this is the water. It's all
like it has the volume. It's only displaced by it.
Potato.
I don't know how to explain
I don't understand that equation. It looks like a different language. I don't know what it's saying.
Density, rose density.
Hold on. Give me 1 second. Sorry. Okay. Alright.
So it's the density of the fluid multiplied by the volume displaced. That's how much fluid was moved aside by the object. And then G. Starts you out.
Then I've changed my answer.
All right then.
Yeah.
It's just not me. I know, I'm fairly sure that it's not me.
Okay, let us try this again. So put in the answer a second time here. See if we got better or worse. And then Eric already knows. Pressure's on him. I hope Candace explained it to you adequately and I gave you time for that. All right, everyone's answered in timely fashion. And we ended up with 0, 1, 4, and 13. Eric, let's hear your answer.
Shouldn't it all be the same since they're all the same weight?
Okay, so you said they're all the same because they're all the same weight. The answer is no. The answer is no because when we look at the equation in red, the one for buoyancy, I'm going to stick with Eric here. Let him work his way through this. They all have the same G, so that's not a concern, right? And they all have the same density of fluid because they're all in water. So that's not a concern. So the only concern is which one is going to displace the greatest amount of water. And so if they're going to sink, they're going to displace a volume equal to their own. So the question really comes down to which one is the biggest, which 1 kilogram is the biggest. So if we look at the densities,
This would be aluminum.
it would be aluminum. And what's the reason it's aluminum?
This is the lowest density.
It's the lowest density, so it's going to have the biggest volume. So the correct answer here was the one person, and I won't ask who the one person was who stuck with the right answer, but kudos to you. So the one with the lowest density, as long as the density is greater than water. If the density is less than water, what's going to happen? It'll float. Because if the density is less than water, then this number here is going to be a smaller number than you would get with this if you replaced the volume of the object with the volume displaced. And so it's not going to sink down and have a net upward force. And so what's going to happen is for it to float, the force buoyant will equal the force of gravity, which means density of the fluid times the volume displaced times G equals density of the object times the volume of the object times G. You can cancel the G's, and you have a relationship between the density and the volume. Given the fact that volume displaced is always less than or equal to the volume of the object, then the density of the object must always be greater than or equal to the density, not volume, of the fluid. Whoops, not greater than, less than. Less than or equal to the density of the fluid for it to float. So that's why less dense things float on more dense things. Question, Candace.
So the homework question about the gold, like the better gold would have less water displacement because it's more dense.
If it's more dense, it's going to displace less water for the same mass. That's correct. And so it'll have a smaller buoyant force for the same mass. I don't remember the question, but your statement was correct. And if I get to a homework problem as I'm going through here, and I don't mention what you think you need for it, bring it up, because we're running behind. So the idea of floating is when the buoyant force is equal to the force of gravity, something floats. The picture on your right here shows how a boat floats, how you float your boat. You float your boat by having it displace enough water to make the buoyant force greater than the downward force, the force of gravity of your boat. Now you make a boat out of steel. Is steel more or less dense than water? It's more dense. So steel should sink in water, right? But if you make it have a bigger volume by creating a cavity, then it can displace more water than it would if it was just a solid chunk of steel. And that's how you make it float. So the boats are hollowed out so that they displace more water than just the material would. And of course, I said that boats are made out of steel. Not all boats, some are made out of wood. There's one that just took its final breaking in California, the cement ship. We used to take South afternoon walks down the beach from Monterey Bay County to the cement ship. And the cement ship was somebody's idea. You know, cement is less dense than steel, so they were thinking maybe we can make a lighter boat carry more payload. Problem is, cement is not as strong. And it was, I always thought that it was actually in the bay and got broken, but no, it was purchased and used as an amusement item until a storm came and broke it. And then it was still out there as an amusement thing, just not official. You didn't have to pay money to go out on it. But now it's broken again. Very sad. So you can look up the cement boat. That's what we call it. Cement ship. Gas pressure. The air pressure, the pressure of the air on me is caused because the air is filled with molecules. Little things of like O2 and N2, nitrogen. And those things are flying around and hitting me. And if they hit me, they're going to bounce off of me. And so they're going to change momentum. And for something to change momentum, there has to be a net force acting on it for a certain amount of time, right? An impulse. And so I have a force on me because of the molecules bouncing off. And the combined effect of all of those molecules bouncing off of me is what makes the air pressure on my body. And if I put my hand in water, it's the same thing, except for now there are water molecules bouncing off of me. So we feel the pressure both in gas and in water because of molecules bouncing off of us. And here is something that's technically from yesterday's lecture, because that's how far behind I am. I don't know. The temperature is a measurement proportional to how fast those molecules are moving. I would be willing to bet no one here knew that. When you measure the temperature, what you're really measuring is how fast the molecules are moving. And so if molecules are moving faster, if they have a higher temperature, what does that mean about the momentum when they bounce off of you? Momentum change is going to be, generally, if a ball comes and hits you and it's going slow, is that a big or small change in momentum? Small. If it's the same ball but it's coming really fast and bounces off you, it's a much bigger change in momentum. And so we don't talk about the temperature for a ball. It's what we call a microscopic, right? It's the kinetic energy of the molecules is a microscopic property. And then we make a macroscopic measurement of temperature for the microscopic objects. Whereas with the ball itself is large, and so we don't combine a bunch of big balls that we can see and say the temperature of the balls. We could, in theory, right, because the equations would work, but we don't. She's looking at me with all kinds of suspicion.
It's just confusing. Like, if temperature is a measure of the kinetic, like, energy of molecules, then if you threw something really fast, why wouldn't it burn you? I don't understand.
Well,
Because you can't throw it fast enough for it to gain.
You don't have that skill.
Like, what,
you know how fast the molecules are flying around?
I guess faster than you could bounce a ball. Never mind.
About 300 meters per second.
Yeah, I can do that.
Okay, but most of us can't. Most of us are restricted to a much lower speed. Okay, Haley, what were you going to say?
So my question is, it's actually about like temperature, like air conditioning and stuff. So how does that work? How does it make stuff hot?
Okay, and that's actually at the end of the chapter I'm supposed to be covering today. So if you're heating something up, what you need to do is make the molecules go faster, right? And so if you make a surface that is hot, molecules will come and hit it, and they will gain energy from that surface, and they'll bounce off faster. And that's how you make things hotter.
Wow.
Or you can burn a gas, and if you burn the gas, it's giving off energy. After the burning, the molecules come off faster. Okay, so basic things about gases. If you compress a gas, the pressure will go up. If you heat a gas, the pressure will go up. When you heat it, it goes up because you made the molecules hotter. They're moving faster. If you compress, it goes up because the molecules hit the surface more times per second. And so you have both compressing a gas or heating it up will increase the pressure. Now, just a little practical example. How many people here have used a bicycle pump to pump up their bicycle tire? How many people have felt the temperature of the bicycle pump after they're done? Haley said yes, it's warmer. Based on this, when you're filling up the gas or the tire, you're compressing gas, right? You're decreasing the volume, increasing the pressure, and in the process, increasing the temperature. So it's something that you can see happening as you increase the pressure and temperature, or the pressure and volume, the temperature goes up. Now, this talks about specific relations. Boyle's law. Boyle's law is when at constant temperature, if you change the pressure, the volume will change such that pressure times volume is constant. So if you increase pressure, then volume is going to go down and vice versa. That's what Boyle's law says. So pressure times volume is constant if the temperature is constant. And then we have, I'm just going to write back here, there are a number of laws. There's Boyle's law, there's Gay-Lussac's law, there's Charles' law, and you put them all together and you get an equation that you may have seen. Anybody seen that equation?
Yes.
A couple. This here is called the ideal gas law. It works for gases that we call ideal. Ideal gases, well, are going to be gases that are non-ideal. There's most things are close to ideal gas if they're gas. So the pressure times volume is equal to N being the number of, in this case, moles. And when we get to chemistry, that will make a whole lot more sense. The number of moles, a mole is just a big number of molecules. So it's like saying how many bushels of pears instead of how many pears. Multiplied by a constant and the temperature. Okay, I'm going to skip this question. I always like the question because really you can't suck. When you drink out of a straw, you're lowering the pressure above, but you can't bring the pressure to zero. And you're not pulling anything up the straw. But the atmospheric pressure is pushing on the liquid. As the atmospheric pressure pushes on the liquid, that pushes the fluid up the straw. So when you drink through a straw, you're lowering the pressure on top, and atmospheric pressure pushes it up to you. So on this, the correct answer was no. They reduce air pressure in the straw, and atmospheric pressure pushes the soda up. That's what you would have said if I would have given you a chance to answer. I did not give you the chance to answer. Jocelyn's like, I can't believe I lost points here. This comes from Pascal's principle. Blaise Pascal came up with the idea that when you increase the pressure at one point of fluid, the pressure increases everywhere by the same amount. So you have fluid, and in the example here, you have atmospheric pressure on the top, and the atmospheric pressure then, if you go down lower, it's higher because change in pressure with rho GH. You come back up, and the water level would be the same inside the straw as outside in the air because the pressure would be the same. But then when you lower the pressure inside, then the atmospheric pressure pushes it up. I see I only have 2 minutes left. Pascal's principle explains how we can make hydraulic lifts. Larissa, this is the time when I have to get to, what was the question you were asking?
It was about when water doesn't flow out when you raise the fill glass above the water line.
Okay. Good, because it does relate to this principle. So if I have a filled glass, let's just draw the picture to go with that. So I have a glass, a tumbler, if you will. Here's my liquid, nice red liquid. And I put my glass in here, and first I put it sideways so it filled up completely with water. So it's completely submerged, filled with water. Everybody with me?
Yes.
And then I take it and I raise it up so the bottom is still under the surface. So it's still water all around, but now I have water going up inside. And the question is, why doesn't the water come down to match the level? We have that water inside, and at the top, you would have pressure pushing down because of the pressure on the top, right? And as long as that pressure is bigger than 0, it's going to stay filled because you have the water pushing up on the bottom, you have the weight of the water that's up above, but then you have the pressure on top, and if you look at the net force that's acting on the water in here, so if I look at the net force, I have the force of gravity down, the force of pressure pushing it down there, and the force of pressure pushing up there, but it's higher pressure down below. And I would have to raise this up to a height that would make the pressure at the top 0 before I'm actually going to have a gap form. We call that a vacuum when the pressure is 0. And so the question then becomes, how high would I have to raise this cup? How tall would the cup have to be before the water level actually does drop? And so given that I have to get it so the force of pressure up here is equal to 0, I'm going to have change in pressure is equal to rho g h, and the change in pressure has to be 1 atmosphere. 1.013 times 10 to the 5th pascals is equal to 10 to the 3rd kilograms per meter cubed, multiplied by, I'm going to use 10 because I can do the math quicker in my head, 10 meters per second squared times h. So these two numbers are 10,000. Divide 1.013 times 10 to the 5th by 10,000, and I get roughly 10 meters. Remember 10 meters, the depth you need for 1 atmosphere? So 10 meters would be a really tall glass. We use barometers, we use mercury instead of water in them, but it's the same principle. The pressure at the top of the barometer is 0, and you only have to have a column that is 10 meters divided by 13.6 because the density of mercury is 13.6 times the density of water. It comes out to 760 millimeters or 76 centimeters for the column you need in a mercury barometer.